This is Second Breakfast, Implicit and Mutation-Based Serialization Vulnerabilities in .NET. I'm Jonathan Birch. I hack Office for Microsoft. If you'd like to talk to me about this presentation or anything else security-related, please contact me on Mastodon. In this talk, I'm going to describe remote code execution vulnerabilities I found in several .NET NoSQL engines. I'll describe what I'm calling a mutation-based serialization vulnerability. I'll tell you some techniques for bypassing serialization binders that people usually use to secure serializers. And then I'm going to tell you a way to use mutation attacks against BinaryFormatter to bypass serialization binders there. That's based off of new research I've done in just the last couple months. And I'll also tell you how to defend against all of those attacks. To give a bit of background about what led to this talk, part of my day job at Microsoft involves doing a lot of security design reviews. So 6 to 8 times per week, I have a meeting where I'm looking at a data flow diagram about some product or feature I've never heard of before and telling people how they could design it more securely. And something I try to do in those meetings is I'll also open their repo, look at whatever code they've already written, try to identify security anti-patterns or vulnerabilities they've already introduced, so I can discuss those with them too. So I've gotten a lot of practice at having maybe 30 minutes to figure out where the vulnerability is in some giant repo. And it's happened that I've done this enough now that I've started doing it outside of work for fun. So the year before last, I saw this article on a certain orange-colored website. This is an article about LiteDB. LiteDB is a .NET NoSQL database. And so I thought, well, I'll look at their repo. It's open source. And when I did that, I pretty quickly found this code. And what jumps out about this code is this line, this call to type get type that's being passed a string. Now, when I see that in any repo, that makes me unhappy. That's a really bad sign. But why is that bad? So type get type in .NET is a method that's used to take a string that's the name of a type and convert it into a type object, the type object that you've just named, essentially. And usually when an application is calling type get type with a string, what they're doing is they're setting up to make an object of that type, and that probably means they're either doing some sort of sketchy marshalling or they're writing their own polymorphic serializer. And so the scenario here is essentially that you've got some user providing you a string that says what type your application is going to make. And if a user can choose which types of objects your application is making, they can tell your application essentially what code to run. So if a malicious user comes along, they can give you bad code and bad things are happening. But let's look at the bigger picture here again. Let's look back at how LiteDB uses type get type. So LiteDB is a .NET NoSQL engine. So NoSQL engines in general, as far as databases, you're not giving them records, you're just throwing objects at them. So an application using LiteDB says, store this object with this index, maybe with these extra properties. And what LiteDB is going to do is it's going to take that object and it's going to serialize it into a BSON stream using their own serializer called BSON-Mapper. And when the application says, okay, I want the object back, then LiteDB is going to deserialize that BSON stream with BSON-Mapper to create that object again and give it back to the application. So that BSON that LiteDB is creating from the objects that it's storing in a file somewhere, BSON is just a binary encoding of JSON. So you can decode it back into JSON and look at it. And if you decode the BSON that LiteDB creates, it looks sort of like this. And if you look at this JSON, there's this underscore type key followed by a .NET type name. And what LiteDB is doing with this is when it's going to turn that BSON back into an object, it calls type get type, it passes the value for that type key to type get type to create the object of whatever type that set is going to be in the database. And that means that BSON-Mapper and LiteDB in general is just a polymorphic serializer, which means that all of the standard vulnerabilities that occur with polymorphic serializers occur with LiteDB. But what are those? Well, I'll give you a little bit of background now on .NET serialization vulnerabilities and why polymorphic serializers are a bad idea. So when I talk about a polymorphic serializer, I'm talking about a serializer where the data gets to describe itself and say what type it wants to be when it's deserialized. So here we have some self-describing data, this box, and it's labeled cat. Cat is the type it says it wants to be. So when the serializer says, okay, I'm going to turn this into an object, it says, well, the label says cat, that's the type. I'll make a cat object, and then I'll look at the contents of this box and set the properties of that cat. And the problem with this is, say you have a box instead that's labeled pain that someone gives you. Well, then your serializer says, well, it says it's pain, I guess I'm making some pain, and you're having a bad time. And to sort of break out of that analogy a bit, pain here is what we're calling a serialization gadget. So In pretty much any framework, in .NET, but also in Java and Python, in lots of other places, there are types where if you create them or set their properties, or sometimes when their destructor happens, they'll have a side effect. They'll do something additional because there's some additional code that runs there. And so serialization gadgets are types where that additional side effect can achieve some attacker goal. And so what you're doing with a serialization exploit is you're trying to get that serializer to create a type that's going to do something you want when you set its properties. If you want a bit more background on serialization exploits in general, I suggest the Friday the 13th talks from Black Hat 17. It's a pretty good primer. But as far as serialization gadgets go, there's a couple I'm going to use a lot in this talk. One is assembly installer. Assembly installer is a .NET type that has a property called path. When you set the path property, it just calls load library on the string you give it. So if you've got a malicious DLL you've been able to plant somewhere, you can just get it loaded, get code injection that way. But an interesting trick with assembly installer is if instead you give it an HTTP URL for that path, it'll go and try to download a DLL from that URL. It won't load it, but it will make that request. So you can use this to get pingbacks if you've got a server somewhere and you want to see if some sort of a serialization payload will work on it. There's also object data provider. Object data provider has a set of properties that when you set them, you get to choose a type, a static method on the type, and a series of string and integer parameters for that method. And when you set all of those, it will call that method with those parameters. So usually this is used to call process.start just to pivot it to shell injection. Okay, so that's how serialization vulnerabilities work at a really high level. Now let's go back to LiteDB and what I'm calling implicit serialization vulnerabilities. So here's an RCE payload for LiteDB. So here we've got some JSON. This JSON looks a lot like that JSON we got out of the bson from LiteDB before. We have this element here that's got an underscore type key, where it's then got a .NET type name for object data provider. That's that gadget that just lets us call any static method. And this JSON is going to call process.start to launch calc.exe. And what we're going to do to exploit this is we're just going to convert this JSON into bson and then tell bson mapper in LiteDB deserialize that bson. And that'll launch calc. Now, there's a trick here because if you look at this deserialize call, it actually has an expected type. And it doesn't matter. So you tell that serializer what type you're expecting, and what's going to happen is LiteDB will look at the type that's in the bson stream. It will actually go create an instance of that type, it'll set its properties, your remote code execution exploit will run, and then after all of that happens, it will then see if it can cast that object it created to the type you asked it for. And maybe that cast fails, maybe you get an exception, but it doesn't matter. Your RCE already happened. So the type that you tell it that you're expecting in this deserialization doesn't matter at all. So, okay, I'm showing you here that the bson mapper, that serializer used by LiteDB, is an unsafe serializer, but there's a bigger problem here. So remember, LiteDB uses bson mapper to read its own storage. That means that anything that lets you put like unsafe data or some sort of a payload in the database gives you RCE. And it's worth noting that a client using LiteDB doesn't know it's using a serializer probably. You're almost never going to call bson mapper. You're just going to tell LiteDB, store this object or give me an object. But clients that use LiteDB are still vulnerable to RCE because that serializer is there. And there's a few different ways that comes up. First of all, LiteDB stores the database as a local file. So if you go look on GitHub, you can find lots of applications where they're just trying to use LiteDB to create some sort of a file format. Maybe they're like a word processing application. They use LiteDB to actually write a document format. Or there's games out there that use LiteDB to create save files. If you provide a file that's opened with LiteDB, it can just do code execution when it's opened. So that's problematic. But LiteDB is also a NoSQL database, so it's got queries. So if you can manage query injection, you can put a malicious record in the database and also get RCE that way. And there's an additional sort of interesting way you can get RCE out of this that I will come back to later because I discovered it later. So, okay. This is a pretty bad vulnerability and a somewhat significant open source library. And what do you do when you find one of those? Well, you look at all of the other libraries that are similar and get exactly the same vulnerability. So here's exactly the same vulnerability in MongoDB. So here we've got some JSON, and this JSON says what type it wants to be. It says it wants to be an object data provider. Note that the key name is different, but it doesn't really make a difference. We're going to again call process.start to launch calc. And what we're going to do here is use MongoDB serializer. So we're going to turn this into bson and then just deserialize it with MongoDB's bson serializer, and that will again launch calc. Now, there's an important difference here because this type matters. So MongoDB, when it's doing that deserialize, it will check that the type the data says it wants to be is assignable to the type you asked it to get out of the deserialization before it creates it. So in order to exploit this, you have to have something open-ended in the expected object graph. Whatever you're trying to read with your application from the database has to have a member in it that you can fit a serialization gadget into. But because this vulnerable serializer is there, MongoDB has these same implicit serialization vulnerabilities. So like LiteDB, with MongoDB, if you can get a malicious record into a database that then gets read, you've got RCE. Because MongoDB is often used in a client-server fashion. You can have one client write a malicious record to a database, a different client reads it, and you're getting RCE on that other client. Also, query injection lets you put malicious records in the database. That also lets you get RCE. Like I was saying, assignability is checked, which makes it a little more difficult to exploit, but in practice, it's actually usually not that hard. So if you go looking at the sort of data different applications put into NoSQL databases, it's pretty common that somewhere in there, there's a type that has a member of type object or dynamic, or like an interface member where you can fit something pretty open-ended into it and you can get an RCE payload to work there. I will say I was only able to exploit the .NET version of MongoDB. There's a Java and Python driver. I looked at them, I tried, I couldn't make it work. I won't say it's not possible, just that I couldn't get an exploit to work. So that's two NoSQL engines, and here's a third. So here's an RCE payload for RavenDB. RavenDB is another .NET NoSQL engine. And here again, we've got some JSON. It says what type it wants to be. It says it wants to be a Windows identity. Windows identity specifically is an RCE gadget for JSON.NET serialization. And it specifically has this claims identity actor property such that when you set it, it's going to get deserialized with BinaryFormatter, and then you can do a BinaryFormatter exploit. If you want more information on that, I suggest looking up the Windows identity gadget on Serial. But what we're going to do with this JSON is we're going to actually make a connection to the RavenDB database server and just make a put request to stick it in the database. So RavenDB, despite being a NoSQL engine, lets you also just write the JSON that's representing the objects directly. So you can write or read JSON, or you can write or read objects. So if you write the malicious JSON and then read it as an object, that gets you RCE. And so because RavenDB has a vulnerable serializer that it's using to read its storage, it also has implicit serialization vulnerabilities. It's just using JSON.NET with unsafe settings. So anything that's a serialization gadget for JSON.NET works. So if you can write a malicious record to the database, someone else reads it, you've got RCE. If you can do query injection, you can write a malicious record, you get RCE. And that special method I mentioned for LiteDB also works for RavenDB. It does care about assignability. You have to figure out a way to get your payload to fit into what the expected object graph is. So like what the application is expecting it has to fit in there. But like I was saying with MongoDB, it's usually not that hard to do. And NoSQL is not just databases. So once I got into this research, I looked at other things that were NoSQL. So here's an exploit for ServiceStack.Redis. ServiceStack.Redis is a NoSQL front end to a Redis cache. It lets you read and write objects to a Redis cache. And what we're doing here again is we're saying what type it wants to be. This will be an assembly installer. That's that gadget that lets you call load library. We're setting its path to just a malicious DLL. This could be a URL to your server somewhere. And what we're going to do with this is we are just going to write it to the Redis cache. When it gets read as an object later, that'll be RCE. So ServiceStack.Redis is also vulnerable to those implicit serialization vulnerabilities. And it's worth noting again that the actual type you're asking for matters. So most NoSQL engines, when you're telling it you want to get a certain type out of the database, it will do this assignability check. ServiceStack.Redis is one of those. So again, you've got to fit your gadget into the expected object structure. But ServiceStack.Redis is exploitable if you as an attacker can write malicious data to the Redis cache that later gets read as an object. Or if for some reason your application just uses the ServiceStack.Serializer directly to deserialize user-provided data, that's exploitable because ServiceStack has a built-in unsafe serializer. And that extra pattern that I keep mentioning will work here too. And now I'll explain how I found that extra pattern. So there was one other .NET NoSQL engine I looked at, and that was MartenDB. So MartenDB also uses JSON.NET with unsafe settings to read and write to its storage. So it should be exploitable. That's the same pattern that we saw with RavenDB. But in RavenDB, you could just write JSON to the database. MartenDB doesn't let you do that. It just says you can give it objects or you can get objects back. So I tried just trying to store serialization gadgets directly as objects into the database, and it always choked on every one I tried. It has one problem or another with them for each one, so then I just came up with a different way entirely to attack it. And that's what I'm calling a serialization mutation attack. So here is a serialization RCE exploit from MartenDB, and this is kind of weird. So I'm going to create in .NET, in C# a dictionary that maps a string to a string. And I'm going to put two things in that dictionary. The first one is going to have a key named $type, which is that type specifier for JSON.NET, and it's going to have a type name in it. This is a workflow designer. That's another JSON.NET serialization gadget. It's got a property on it where when you set it, you can just get it to do an open-ended XAML parse, and in general, parsing untrusted XAML gets you RCE. So the second entry we're putting into this dictionary is just that XAML payload. And what we're going to do with MartenDB is just store that dictionary in the database, and that gets us RCE. We just stick it in there, and when it gets read again later, that code will execute. And that feels really weird. We're putting a dictionary in the database, and when we read it back, it's going to run code, and why is that? So MartenDB is using JSON.NET to read and write its storage. So let's look a little bit on how JSON.NET serialization works for a dictionary like this. If you've got a dictionary mapping a string to a string, then let's say you have like a key named fruit and a value named pear, and you serialize that. What JSON.NET will do is it will just use that key name directly as the key it uses in the JSON it produces. So whatever your key names are in your dictionary, those are the key names that actually get put into the JSON. Now, if you compare that with what a serialization payload looks like for JSON.NET that gets you RCE, like this, you've got this $type key that's going to be the type specifier. That's telling JSON.NET what type that JSON is going to turn into when it's deserialized. And the important trick here is that there's nothing special about that $type key. So there's nothing that prevents you from making a dictionary where one of the keys in the dictionary is named $type. And if you serialize the dictionary where one of the keys in the dictionary is named $type, JSON.NET will just output a key called $type with that value you gave it. But when you deserialize it, that's going to tell it what type of object it's going to make. And this means that it's going to mutate into that type of object when it's serialized and then deserialized. This doesn't just work for dictionaries. This works for anything in .NET that has a key value structure. So dictionaries, hash tables, JObjects, expando objects, and like 20 other types that nobody uses. But this pattern, this ability to have data that mutates into an RCE payload, opens up a lot of attack patterns that aren't traditionally considered possible. So let's say you have an application that just has a web form that lets you put some key value data into it. This is a screenshot of an application you may or may not recognize that lets you put key value data into it. This is not one that was vulnerable to this exploit, but I can say that this gets stuck into a dictionary. And what we're going to do here with this key value data in this web form is we're going to put one of these payloads into it. We're going to say, okay, the first key value pair is $type and then name of a .NET type assembly installer. And the second one is going to be a path that's a URL to our server so we can see a pingback happening. We make a form post with that form. And on some web front end somewhere, that gets stuck into a dictionary or a hash table. Then it's going to get serialized, let's say, with some sort of unsafe serializer like JSON.NET into a database or a cache. Later on, when it gets read from that database or cache, with that same unsafe serializer, it's now an RCE payload and code executes. So here you've got a serialization exploit where you never got to touch the serialized data. The application serialized the data and deserialized the data, but because you were able to put some malicious strings into that data that gets serialized, you still get RCE. And this is that extra pattern I've been mentioning for all of those NoSQL databases. So here's essentially that exploit against LiteDB. We're going to make a dictionary mapping a string to a string. We're going to put key value pairs in there, so we've got that underscore type key, which is LiteDB's type specifier that says what type it's going to be when it's deserialized. We're setting a path. And all we're going to do with this dictionary is we're going to stick it in the database in LiteDB. If you just store that dictionary in LiteDB and then it gets read out later, that gets you RCE. And this is kind of a ridiculous exploit because LiteDB also doesn't care about assignability. So if there's key value data anywhere in any object that gets stored in a LiteDB database and an attacker can control any key value pair in that dictionary or whatever it is, that's enough to get RCE. They just have to be able to give you 2 strings, and you stick them in a database. And this works for a lot of serializers in .NET. Here's a list of all the ones I know of. There's different requirements to get an exploit to work. Some of these are hard to exploit. Some of them are really easy. And you'll notice that there's both the NoSQL engines, but also the serializers themselves. So JSON.NET is exploitable. JavaScriptSerializer is exploitable if you have a simple type resolver. There's an addition at the bottom of this list. BinaryFormatter is exploitable. Last time I talked about this sort of thing, I didn't think so, but it is. I was not able to figure out a way to get mutation to work with MongoDB. I can't guarantee 100% it's impossible, but it's a lot harder to pull off. This sort of attack has a lot of limitations. So depending on the particular serializer you're looking at, it can be harder or easier. JSON.NET attacks only work if you're using JSON.NET with unsafe settings, so you've set type name handling to something other than none. But you also have to control the first key value pair in something, in a dictionary or a hash table. If that type key shows up later on, it's ignored. And when you serialize it, you have to serialize it in such a way that JSON.NET doesn't double the keys. So sometimes when you've got that $type key in your dictionary, it'll put another one in there, and that'll just break everything. It really just requires experimenting with different scenarios to figure out where that will happen or not. But some serializers, this is really easy. Like I was showing you, LiteDB is very easy to exploit. So is JavaScriptSerializer. If you're using JavaScriptSerializer with a simple type resolver, it's really easy to exploit. You just need to be able to control 1 key value pair in a dictionary somewhere, and that's good enough. It'll actually put that key value pair first when you serialize it, so it will conveniently always get URCE. You can actually scan actively for this sort of vulnerability. So that example I was showing with a web form where you're putting key value data into it, you can do that in general. If you've got some sort of .NET application on the web that's got an API or a form or something that takes key value data, you can put that assembly installer payload in there, give the URL to a server you control, and if it gets deserialized later, you'll get a ping back, and you can just scan for this sort of exploit on surfaces out there on the internet. This is also useful for dynamic scanning inside of your organization. So if you want to defend against this sort of attack, and this is something I'm going to say a lot in this presentation, use a safe serializer. Use a serializer where the data doesn't get to tell you what type it wants to be. Use a serializer that doesn't do any sort of polymorphism. System.text.json.json serializer works really nicely for this, but people like polymorphism, so it doesn't get used as much. You can also use a serialization binder to secure things. A serialization binder is going to let you decide what types are allowed to be created during deserialization. That said, the next section, I'm going to tell you how to bypass serialization binders, so definitely a grain of salt with that recommendation. So, bypassing serialization binders. So, I mentioned serialization binders in that last slide. In general, a serialization binder is going to be a type that you can define, which implements a method called bindToType. And what that method is going to do is every time a type is going to be created during deserialization, it'll ask you, is it okay to create this type? And then you can either say, yes, here's the type for that type name you gave me, or throw an exception. So if you're doing it right, you can create an allow list, and the serialization binder acts like a filter. So when you're taking this maybe untrusted data and deserializing it, you get to say, well, okay, cat I know about. Cat is in my allow list. I'll make cat objects. Pane, I don't know what that is. I'll throw an exception. And then you never make a pane object, and things are a little bit better. The problem is nobody writes these correctly. So this is the right way to write in a serialization binder. This is a strict allow list based off of the strings for type names. And if you run into a type name you don't recognize, it throws an exception. But a lot of times when I see serialization binders in code, they look more like this. So this serialization binder, what it's saying is, okay, I've got some DLL or assembly I've written. I know all of the types I put in that aren't malicious serialization gadgets or dangerous things to deserialize. So I will say every type in my DLL is just allowed by the serialization binder. And the trick is this is almost always exploitable. This will almost always be something you can bypass to get RCE. The reason for that is because, in part, generics. So say you've got a type in that trusted assembly that looks like this. This is initialized list. It inherits from the .NET list generic, and it just adds an additional property called isInitialized that's a Boolean. This seems like it should be pretty harmless, but that serialization binder I was showing you, where we're saying everything for our trusted DLL is okay, you can actually exploit with this. Here's how you do it. So here's a JSON.NET RCE payload that bypasses that serialization binder using this type. So the type that this says it wants to be is an initialized list. Inside of the template for that generic, we've got assembly installer. But when the serialization binder is asked about this type, it's asked about an initialized list with that internal type. And this comes from your DLL, so this is allowed. Initialized list is in your DLL, and it doesn't matter what's inside of that generic. But even though assembly installer is not itself listed independently as a type here, the serializer can infer the type because it knows this is a list of assembly installers. So when you get to the values array and you're saying, okay, I'm going to actually create elements for this, well, it's going to create assembly installer objects. And when you set the path on one of those values, when you're setting the path on an assembly installer, and you've got RCE. It's interesting to note that this is not what JSON.NET will serialize if you serialize this object. If you serialize this object, it will actually put the assembly installer type there in the values list. But if you don't put it there, it's fine. It can figure it out and it doesn't care. And so the key thing to understand here is that your serialization binder is only ever going to get asked about types that are directly mentioned in the serialized stream. This gives you other ways to bypass serialization binders as well. So here's a technique I'm referring to as a contagion attack against serialization binders. So say there's some specific type you're trying to block. You have a list of serialization gadgets you know are dangerous that you're going to just make a block list for, because that's easier than making an allow list for your application. Well, JSON.NET and lots of other serializers only care, like I said, about the types mentioned directly in the serialized stream, but all of your types have members. They've got constructor arguments, they've got properties, and all of those things have types too. And you can mention those types, but you don't have to. The serializer can figure them out. So if you can create situations where the serializer can figure out that there's something that should be a type that's dangerous, it won't ask you about it, it'll just go make it. So if you've got some sort of type that's dangerous, and it's the type of a member of some other type, then you can deserialize that other type. And because you've got that member in there, it'll make an object of that dangerous type as well, but it won't ask you about it. And that chains. So if there's something you can use for a serialization exploit that's a member of a property, of a constructor argument of some other type, that's good enough to actually get RCE with it. And here's an example of that. So the Windows identity type I used earlier, that's an RCE gadget for JSON.NET. It lets you pivot to BinaryFormatter. And let's say you've got a serialization binder that says, okay, we're going to block Windows identity. We know it's dangerous. What other types are there that let you get that in there? Well, there's the Windows authentication event args type in .NET, and it has a constructor argument called identity, whose type is Windows identity. So if you deserialize a Windows authentication event args type, that's the only type your serialization binder gets asked about. But when you deserialize that identity property of it, it won't ask your binder, do you want to make a Windows identity? But it will make a Windows identity object. And you can set the properties of it, which is good enough to get RCE. So if you're going to try to create a block list, you have to create a block list that considers every type that might contain the types you're trying to block. And it turns out that's kind of impossible. So serialization binders that are block lists do not work. And with all of that as background, now I'm going to tell you how you can use mutation attacks against BinaryFormatter to bypass serialization binders there. So when I've talked about this issue before, I was of the belief that BinaryFormatter was safe from mutation. It should be. BinaryFormatter does not serialize to a text format. It serializes to a format called MSNRBF, which is an awful format, it's binary records. So it's essentially a bunch of records that say, okay, here's a byte that's a record type. The record type is the length of the rest of the records in this thing, that sort of deal. And you've got elements in there that are like, here's a record that's the actual type information for an object, but there's a different record that's the data for the object. So the key here is that when we've been doing mutation attacks against like JSON or BSON payloads, the problem is that some of that data can suddenly be the type information for the object. You can have some key value pair in there and the data is turning into sort of the metadata. But that shouldn't be able to be possible with BinaryFormatter because the metadata is kept separately from the actual data. But interestingly enough, while I was last talking about this set of issues at DEF CON last year, a member of the dev team at Microsoft was opening a bug about BinaryFormatter. So Lottie Prosek on the dev team opened this bug: BinaryFormatter serialization does not round trip with I-convertible fields. And this is a really neat bug, but it's kind of complicated. So to go into what that's about, if you're serializing an object with BinaryFormatter and that object has a member whose type is an interface, But what you've assigned to that interface member is essentially a boxed value type, a primitive type. So you've got an interface member where you're just throwing an integer in it or a string or something like that. Binary formatter doesn't serialize that correctly. It doesn't create MSNRBF. What it does instead is it just takes that byte or the bytes for that primitive type and sticks them directly in the stream with no metadata. So instead of having these records that say, okay, we're going to have an integer here, the integer has this many bytes, and then here's the integer data, it just says, here's the integer data, which means that all of that metadata is just not present. And that means on deserialization, when it's trying to read those bytes, it's expecting that MSNRBF, and instead it's just got the bytes for your string or integer or whatever. And that means that a lot of scenarios are just going to break. So here's a basic proof of concept that lets you sort of repro that bug. Here we have a class. It's got a member with an interface type, this iConvertible conv, and we're just going to stick 5 in there for the value of that. When we serialize this, that 5 is just going to get written directly to the serialized data, and then when you try to deserialize it, well, it's going to say, well, 5 doesn't make sense here as MSNRBF metadata, and it's going to throw an exception. So, okay, that's a functional bug that's problematic for someone, but this is a security conference and this is a security talk. So how is this a security bug? Well, I'm going to show you a very slight modification of this code. Here we again have that type that has an interface member, this iConvertible. And instead of assigning 5 to it, we're going to assign a very carefully chosen uint64 value, that number. And then for the second element in this object, because that matters too, we have just an object member, and we're going to put a byte array in it. And when we serialize this and deserialize it, we don't get an exception. Instead, what happens is it will launch, well, yes, there's a suspicious byte array. We don't get an exception. Instead, what happens is it will launch calc if you serialize that object and then deserialize it. So this particular exploit was discovered by Levi Broderick on the .NET team. He has given me his blessing to explain it here, but I want to give him credit because this is pretty cool. And that byte array, I've truncated it in this slide. If you want to get a picture of it, here's the whole thing. I've also put it on my Mastodon if you want to copy paste it rather than typing in that whole giant mess. But I'll explain how that exploit works here. So that uint64 value, that's actually valid MSNRBF. So before I was saying that when BinaryFormatter tries to serialize something like a uint64, but it's assigned to an interface member, it doesn't put the metadata around it. It just sticks that data straight in there. So this integer value is actually valid MSNRBF. And what it's the valid metadata for is a string of a specific length. In particular, it's a string that's long enough such that when BinaryFormatter is reading the bytes from the stream to deserialize, it will read the next few bytes of metadata as part of the string. So when this gets read, it consumes the next set of metadata, which means when it starts trying to read more MSNRBF for the next object, it's actually reading in the middle of that byte array. And the contents of that byte array are more valid MSNRBF. And that's actually the serialized data for essentially a binary formatter exploit. So the object graph you get when you deserialize it looks like this. You have a string. That string has a bunch of nonsense data in it because it's just consuming that metadata that wasn't supposed to be a string. But then you have a sorted set, and that sorted set has a confused delegate exploit. A confused delegate exploit is a classic way of getting RCE out of binary formatter. James Forshaw talked about this in his Are You My Type talk, but it's also there on Why So Serial. So, okay, that's interesting. It's kind of weird that that works. This pattern really isn't exploitable, though. So, okay, if you imagine this scenario where, okay, there's an application somewhere and it's letting you provide the value for that uint64 and the contents of that byte array, and then it's serializing them like this and then deserializing them with binary formatter. Yes, that gives you RCE, but that application would never work except when you're giving it RCE payloads. So no one has an application like that. It's also worth pointing out that binary formatter has been around for a long time. This bug has always been there, and it was only discovered last year because no one ever does this. So that scenario, as I just described it, is not exploitable. But that does not mean binary formatter is safe. So I was just showing you that binary formatter will serialize things incorrectly when you're assigning a value type to an interface member. But that doesn't mean there isn't a way to serialize that data. So you can create MSNRBF such that it means here's an interface member and we've assigned a boxed value type to it. And if you create that data, binary formatter will deserialize it, but you can set it up so that when it's serialized and then deserialized again, now it's an RCE payload. So you have this flow. You're providing serialized data to an application somewhere. It deserializes it. It gets a uint64 and a byte array. But if it serializes and deserializes it again, now it's RCE. So you have an attack pattern that looks like this. You've got a web front end somewhere where it's expecting data that's serialized with BinaryFormatter. And that's not a great idea, but let's say it's going to be deserializing it with a serialization binder. What you're going to do then is you're going to give it data so that when it's first deserialized, it's harmless. It's a uint64 and a byte array. Those are primitive types. Serialization binders don't even get asked about them. They just go by. And so then it gets that uint64 and byte array, but say it's going to take that object and then serialize it again. Like it's going to put it in a message queue or a cache or viewstate, because of course viewstate just uses BinaryFormatter behind the scenes to do writing and reading. When it does that, it's going to turn into something else. It's going to turn into an RCE payload that's now just hanging out in that cache or in your view state. So when it gets read again, that payload goes off. This is cool, but it's also really hard to pull off. So this exploit only works if you have that pattern of deserialize, serialize, deserialize again. Also, because BinaryFormatter cares about assignability, there's only a handful of interface members or of interfaces that you can actually use for this. The only interfaces you can assign a uint64 to are iComparable, iFormattable, and iConvertible. That doesn't show up a lot in expected data, but there's kind of a trick here. Say that web front end that's expecting BinaryFormatter serialized data, say the object graph it's expecting has some sort of an open-ended member in it. Say it's got some member somewhere of type object. And they're saying, well, that's okay. That's not going to be a problem because we've got the serialization binder. So the serialization binder will mean that whatever that object gets assigned, it can't be something dangerous. Well, in that case, what you assign to that object is tuple. And then the types you put in the tuple are iComparable and either object or a byte array. And then inside of that tuple, you put that magic uint64. You put your byte array that's got your serialized payload. When it gets deserialized, the only type the serialization binder gets asked about is tuple. And it says, are you going to allow tuple? And maybe the serialization binder allows that. And that works for all of the other like generic types that let you collect types together. So key value pair, for example, also works for this. And then it gets by that serialization binder. And if you've got that serialized and deserialized again on the back end, you've got an exploit. So that's a lot of problems. What if this has already been fixed? What if this do you not have to worry about so much? So MongoDB made a pretty good fix for this. Like I reported all of these issues to these NoSQL developers and so on. MongoDB made a fix where they actually made it so you have to now give an allow list for the types that can get read from the database during deserialization. And this is not so great for application developers because they have to make a list of all of the types that they want to read from the database in their application. But it means that I don't know a way to exploit this anymore from MongoDB. LiteDB made a fix where they now check assignability. So if you use a more recent version of LiteDB, that whole business where it doesn't care what type it's expecting, it will actually check that it's assignable first, which puts it sort of on par with those other NoSQL engines. And then all of these engines, except MartenDB, also added a block list, a list of types they're saying, well, we don't want to deserialize this because we know it's a serialization gadget. But remember, I showed you how to bypass block lists. Block lists are worthless, so that doesn't do anything. MartenDB did not do anything. I contacted them. They sent me a lot of emails saying we probably should fix this. Last I checked, they still haven't. So it's just like that. It's maybe not a good idea to be using any of these except Mongo at this point, honestly. JSON.NET, because JSON.NET itself has this mutation issue, won't be fixed. I talked to James Newton King, who is the maintainer of JSON.NET. He actually works for Microsoft now. He said it's essentially supposed to do that. Don't use JSON.NET to serialize with unsafe settings if any user data could be going in there at all. So that mutation is just going to stick. That's just how JSON.NET is going to work. JavaScript serializer won't be fixed. The .NET folks said don't use simple type resolver with JavaScript serializer, essentially. So they're not going to fix this. If you're using JavaScript serializer with simple type resolver, don't. You've almost certainly got RCE vulnerabilities. BinaryFormatter will not be fixed. BinaryFormatter is deprecated. .NET has said they're not going to fix that bug, even though it's technically a functional bug in the serializer. They want you to just not use it. There's other good reasons, to be fair, not to use BinaryFormatter. Well, okay, that's a lot of problems. How do you prevent this from being an issue in your application? What are some best practices to avoid these issues? First, the thing I keep saying, don't use polymorphic serializers and don't write your own. So if there's a serializer where you can just stick whatever types you want in it and then get them back out of it, and you don't have to make an allow list, it's dangerous. Don't do that. Similarly, if you've got a database that does the same thing, a NoSQL engine where you can put things in it like that, it's dangerous. Don't do it. Don't call type get type. If you're calling type get type and putting a string into it in .NET, you're probably making a polymorphic serializer, even if that's not what you think you're doing. In Java, the same thing is true with class.forName. You can do exactly the same set of issues there. Because mutation attacks are a thing, you can't have unsafe serializers even on your back end. Because if user data is going in there and there's just some strings someone can control, that might be able to be something that can turn into an RCE issue. This one kind of hurts, but don't read untrusted data from NoSQL engines. So in general, the pattern with NoSQL that you can stick any object type you want into it and then get it back means that if someone can write a malicious record to your database and then you're going to read it later, that's probably going to give you RCE. MongoDB might be safe. I don't know how to exploit it. All of the other ones seem to not be safe. And this is probably an issue in NoSQL libraries that are not built for .NET as well. If you want a research topic, that's a cool one to go into. I haven't looked at them too much. Don't use serialization binders. Lots of applications out there try to secure themselves with serialization binders. You probably can't write a secure one. It's very, very hard. Instead, what you want to do is re-architect your application so that's not relevant. You shouldn't be using a polymorphic serializer such that you need one. If you are going to make a serialization binder, and I don't like saying this, then if you make it a strict allow list based on strings that only allows pods types, that might be okay. I don't know a way to exploit that as long as you have a binder everywhere. And don't use BinaryFormatter. BinaryFormatter is deprecated. .NET is not making fixes to it. This stuff, I will say, is not just exploitable in .NET Framework. It's exploitable in later versions of .NET as well, so that doesn't protect you. And if you have a serialization binder just on your front end use of BinaryFormatter, you can still get bitten by it because you're using it on the back end because of those mutation issues. And this went faster than I intended, but that's all I had for this talk. Are there any questions at this point? Okay, several. We'll start with you.
Have you tried to exploit any of the exploits on Cosmos DB?
The question is, do I have any exploits for Cosmos DB? I've looked at Cosmos DB some. I have not actually built a proof of concept exploit for it. I can't guarantee it's safe, but I did not see a way to exploit it. I think you're next.
So the gadgets that you mentioned are framework. Are there any for that you use for that?
The question was that the gadgets I've been listing are for .NET Framework. Are there gadgets for .NET Core? There are gadgets for .NET Core. I won't tell you one that gives you remote code execution, but there's quite a few that will at least give you SSRF. I've talked about this previously, and now I'm trying to remember some of them off the top of my head. Let me talk to you after, or I'll put it on my Mastodon. But I know some gadgets that give SSRF I've talked about before. But .NET Core, it's not called that. Well, yes, .NET Core is not safe. It's just that people who are not me haven't figured out how to do it yet, so I'm not giving away too much. Yes.
Have you looked at other serialization systems like Protobuf?
The question is, have I looked at other serializations systems like Protobuf? Yes. There are implementations of Protobuf that are exploitable, and there are implementations that are not exploitable. If you want to talk to me afterwards, I could give you specifics. And I suppose that's it. Well, okay, thank you.